You have things for me. Send them to your left, please. Right now,
I have Thursdays off. Really have
Oh, yeah, I changed my. Honestly, it was kind of fun. It's fun, but it's too much. And she like inspirated so much. And trying to like the line has a positive slope. Which way does it go? Right. 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 See my problem? Right. And say again. Up. Right. Okay, wait a second. But a line goes infinitely in both directions, doesn't it? So if I say up right, I'm also saying down left. Okay. We need to make a convention. I apologize to every lefty in the room. The convention is we think of things going from left to right, because that's the direction in which we write. When this technique came up, that wasn't true. And a lot of this originates in descriptions of lines in Egypt and in Babylon, where it's described vertically, because of the direction in which we write. Hieroglyphs were not written right to left. So if I consider motion like I do writing as going from left to right, then my line is going up. I want to change this phrase. I don't like this phrase. So we'll think of it as what's happening to X. As we go from left to right across the number line, across our graph, X is increasing. So I can think of this as X is increasing, so is Y. If I change this word to say negative instead, what changes down here? Wait a second. If I say as x increases, so does y, then as x decreases, so does y is the same direction, isn't it? That's the same slope. A positive rise with a positive run, a negative run and a negative rise, those go together. That's still a positive slope.
Increases, y, decreases.
Aha. And in that case, I'll change up to down. So now I have a common framework to think about direction of lines. I'm thinking about going from left to right. Am I going up? Am I going down? So let's use those phrases as increasing and decreasing as our idea. I can think of a line increasing as I go from left to right, or a line decreasing as I go from left to right. A curve isn't a line. So we talk about the slope of a curve, we think about the derivative, but the derivative is really the slope of a line. It's the line tangent to the curve at that given spot. So if I think about the slope of f prime, sorry, the slope of f as being the slope of the tangent line, then I can think about the direction of f as being the direction of my tangent line. If I have a section of my graph, the interval from A to B, and I tell you that the derivative is positive there, then all of the tangent lines point that way. Well, I'm just going to go ahead and steal the term. If a line was increasing there, my function will be increasing there. Change positive to negative, I change increasing to decreasing. Now, at this point, I go back to exam 1. And I remember asking you to draw a picture of f prime of x on top of a picture of f of x. And what we did is we said, oh, I can kind of figure out if the tangent line is going this way, I should have a positive slope. And a positive slope means now an increasing function. So we just kind of sketched along, figuring out roughly whether we were positive or negative in different pieces. But here's an arbitrary graph function. If I asked you to draw a picture of this, what shape would you get? My buddy, the parabola. Two options for a parabola. Is the parabola in this question opening up or down? Because the leading coefficient to the x squared is positive. Think about the tangent lines. Over here, my function should be decreasing. Over here, it should be increasing. What's missing from my list of options for f prime here? I have positive, I have negative, I don't have equal to 0. It's not even a vertex. It's a critical number, isn't it? That's what we were looking at critical numbers for. There were places where my derivative was 0. I can use my critical numbers to figure out where this function is increasing and decreasing. Now, just like in the last section, I should be able to look at both kinds of critical numbers. Critical numbers where my function's derivative is 0, and critical numbers where my function's derivative doesn't exist. But this derivative is what's the derivative here? Aha. And that's a polynomial. It's defined everywhere. I don't have to worry about places where it doesn't exist. The only possible critical points are where my derivative is equal to 0. That's the only place this is 0. That means everywhere else this is either positive or negative. By the intermediate value theorem, if you pick any number that's not 5/2, the entire side of the graph where the number you picked is has to be going in the same direction. Here's a number line. There's 5/2. Somebody give me a number, any number at all, smaller than 5/2. 1. Okay. I'm going to put it in a box over on this side. Any number at all bigger than 5/2. Great. Is my slope positive or negative at x equals 1? There's my derivative. What's f prime of 1? 2 times 1 minus 5 is -3. I don't care that it's 3, I care that it's negative. Somebody pick another number smaller than 5/2. Plug in 2. Do you get another negative number? Do you plug it into the derivative? 0. I get another negative number. -16. I get another negative number. Every single number on this side, the left, of 2.5 is going to give me a negative number. It can't change. Why? But I would have to check those numbers. I have to check all infinitely many of them. And I can't do that. I don't have enough time to check infinity numbers.
10 minus 0 is it changing? Or positive?
The intermediate value theorem says if I was going to change from from negative to positive, I'd have to go through 0, right? And the only place we go through 0 is right here. So there's no other chance for me to change other than at 5/2. Means everything on the left is going to have the same sign. Similarly, everything on the right will have the same sign. And if I take 3 and plug it in, I get +1. I don't care that it's 1. I care that it's positive. Which means my function is decreasing, then increasing. And I can write it out as intervals. F of x is decreasing on the interval from -infinity to 5/2. And is increasing on the interval from 5/2 to +infinity. This little sign chart that I've made out of my number line, I'm going to use those a lot. Does that make sense? Wonderful. Questions? Same question. On what intervals is the graph of this function decreasing? On what intervals is the graph of this function increasing? Let's go through the same process. I'm going to start in exactly the same place. Find me some critical numbers. Now I'm going to tell you up front, this problem's rigged. Same as last time. My derivative is a polynomial. Therefore, it exists everywhere. The only kind of critical number I need to worry about is where it's equal to 0. I think I'm going to take out more than just an x. I am going to take out an x, but I can also take out a 12 with it. And if I take out a 12x, that leaves x squared minus x minus 2. And that factors. Yes? Here, that's a 3. Yes, and this quadratic factors. But if you can't factor or you don't factor very well, then you should use the quadratic formula. But this does factor quite nicely. Which saves me some time. Which means I have 3 critical numbers. Either this piece is 0, which means x is 0. This piece is 0, which means x is 2. Or this piece is 0, which means x equals -1. And now I find myself in the same boat. Make a sign chart. Create a number line. Put these on them. It is absolutely important that you put the critical points on the line in the right order. I know that sounds silly. I cannot tell you how many times I've seen it done. -1 is smallest, then 0, then 2. Please put them in the right order. And then I'm going to take numbers in between. And I'm going to use those to test by plugging them into my derivative. And that's why over here on the left, I'm going to write f prime of x, because that's what I'm going into. And I can use any test numbers I want, as long as I pick them in the correct pieces of the line. It is my personal setup to put them in little boxes. You don't have to. Just that was the way I was taught in the 80s, and I haven't changed it since. I do need to specify which number you put in. Yes. I definitely want to see the number you're testing, because the easiest thing to make is a sign error. However, if I'm going to plug in -2, -2 cubed multiplied by 12, -2 squared multiplied by 12, it's a pain in the neck, isn't it? I absolutely can take it and plug it into the calculator. But if I work this out the long way by plugging into the original function, I have to make sure I multiply correctly. But this expression is the same as this one. So I can use the factored version, and that'll help me out. Instead of writing f prime over here on the left, I'm going to add another column. And I'm going to write on each row separately one of the factors. And they each get their own line. And it's a lot easier to plug into just 12x, or to plug into x minus 2, or to plug into x plus 1, than it is to do all the cubing and squaring and multiplying and adding. So I'm just going to plug in directly. -2 times 12, -1/2 times 12, 1 times 12. All I really care about is whether it's positive or negative. I don't care what the number is. But here's the important thing to note. Each of the factors in the leftmost column is a line. Y equals 12x is a straight line. Y equals x minus 2 is a straight line. Y equals X plus 1 is a straight line. They only change from negative to positive once on each line. And that makes my life easier. But to get F prime, I have to multiply all these three things together. So I multiply down, and that gives me F prime. So multiply down each column. Negative times negative times negative is negative. Negative times negative times positive. Positive times negative times positive, and three positives. And I get the exact same result I got up here. But the arithmetic is easier. The textbook actually does this in yet another way. Top of page 298. Here's their version of the sign chart. The only thing they did is they flipped rows and columns from what I did. They have the intervals here. So less than -1, between -1 and 0, between 0 and 2, and bigger than 2. And they've written them as intervals. And then here they're doing what I did across each row. If you like this idea laid out better, go for it. Lots of options available to you. Questions? What's Fermat's theorem tell me? My good old buddy Pierre de Fermat. What does he say? Yes.
If f of x has a local extreme at x equals c, and f of c exists like that, or c equals c.
Aha. Extremes happen at critical numbers where my derivative exists. This derivative existed everywhere, right? And that means these critical numbers are places where I could have extremes. So x equals -1 could be an extreme value. X equals 0 could have an extreme value. X equals 2 could have an extreme value. I can tell what kind of extreme value I've got just by looking at those arrows. My graph, as I go from left to right, is going down followed by going up. What's going on at x equals -1? It's got to be a minimum of some type. It might be absolute, it might just be local, but at least it's a local minimum. What about at 0? I've got a local maximum. And at 2, I've got a local minimum. if my derivative changes sign at a critical number, then depending on which way it changes sign, I know whether or not I have a local minimum or a local maximum. What I don't know is the value. And in chapter 4, section 1, you were asked to give me the maximum value and the minimum value. How do I get the values? Go back into the original equation and plug it in. There is an option that is missing from this list. It could be that f prime does not change signs. Now that means I could see on my table pluses on both sides or minuses on both sides. That's okay. That's allowed. If it doesn't change sign, then I don't have an extremum there. That is f prime. Oh, on the problem we were just doing, let's go back and put the values in. One of these is really easy. The other two require me to actually do the math. If you put in 0, you get 5. What happens when you put in -1? I heard a whisper. -1 to the 4th is positive, so that's 3. -4 times -1, that's +4. -12 times +1, that's -12. +5. 3 plus 4 plus 5 minus 12 is 0. What if you put in 2? -27. Now, a number of you were calculating this multiple times. You calculated it out by plugging in -1, 3 parentheses, -1 to the fourth, and so on, right? And you do the same thing with the 2. I wrote this equation once. Write it in y equals. And then you can use the trace button to find these values. Now, let's characterize each of these. -1, 0 is a local. What did our sign chart say? Oh, -1, 0 is a local min. And 0, 5 was a local maximum. And 2, -27 is a local minimum. Hey, wait a minute. Just going by the sign chart, as I go from left to right, I come down, I go back up, I go down, I come back up, right? It's a W shape. It's a lopsided W, but it's a W shape. Because 1, 0 being a local minimum is hot. It's a W shape. 2, -27 isn't just a local minimum. It's an absolute minimum. Because it's the lowest point in the graph, period. Back in my algebra class, when I talk about polynomials in general, we talk about end behavior. Like on an x squared, both sides go up. And on x cubed, one side goes up and one side goes down. But we're thinking of that as if we're moving from the middle out. Our motion here is always left to right. So even though this is a 4th degree polynomial, and since that's an even number, both ends go up, I'm still thinking of what's happening on the left side as being decreasing. The fact that both ends go up means that whatever's in the middle that's the lowest has to be the lowest overall, because we never turn back around. Let's try another one. To do the critical numbers, I need the derivative. To do the derivative, I need my buddy chain rule. Ugly junk cubed. F prime of x is 3 ugly junk squared. But wait, there's more. Say again. 2x. Now the best part is that's already factored. And it's a polynomial. There's no division, there's no roots, there's no trig, there's no exponent, this is exponential terms, there's no e. I'm really happy to see this because it's a polynomial. It exists everywhere. The only kind of critical number I'm looking for is where it's equal to 0, and it's already factored for me. So either one of those pieces must be 0. I don't worry about the 3 because 3 is not 0. Well, that means here I get x equals 0. What about here? Got to remember to take the square root and get both of them. Build me a sign chart. In order to save a little bit of space, if I were to write this as a multiple line sign chart with each factor on its own line, I would put the 3 and the 2x together. Right, that is 6x. That's easier. Save me one line. Because 3 never changes. I really don't have to worry about that one. But what do I end up with? Yes, I wrote my test numbers down. Aha. I don't know what you're talking about. Don't get ahead of me here. Here's exactly an example. On the same thing on the left as it is on the right, I have a critical number where I don't have a sign change. So -1 and 1 are places where there are not extremes. The graph is going down on both sides. But there's still a place where it's horizontal in the middle. It flattened out. So at -1 and at 1, we have flat spots. At 0, though, we have what kind? I have a minimum, an absolute minimum. Because we're coming down all the time on the left, and then we're going up all the time on the right. That's not just a lowest point, that's the lowest point on the whole graph. Grab your calculators, graph this sucker for me. Since I really only care about what's going on in a small section of the x-axis, rather than look at this on the standard window, where I don't really see much of what's going on, I'm going to change this by zooming in. There we go. See how we're decreasing and still decreasing, but we flatten out in the middle? We're increasing and still increasing, but we flatten out in the middle. And there's my absolute value at 0. 0, -1. Questions? If I think about a graph that's increasing, I can actually draw an increasing graph in several different ways. I can think of a graph like x squared. could think of a graph like the square root of x. Or I could just think of a straight line like y equals x. And I could do the same idea for decreasing. Yes? I could draw a function that's decreasing, either like x squared on the left, or I could turn the graph of the square root of x upside down, or I could turn the line upside down. Pick any 2 points on each of these three and draw me a tangent line at each of the points you pick. So in x squared, I'll pick 1 point over here and 1 point over here. And same thing with x, with a root x. I'll pick 1 point over here and 1 point over here, and same thing with x. If I draw a tangent line, or at least a little piece of one, at each of those spots, in the first two, the slope is changing. The third one, it isn't. Right? Same sort of pictures now for decreasing. If I draw tangent lines at 2 spots, I see the same sort of thing in 2 of the 3 pictures. In these first 2 pictures, the slope is changing. But in the third picture, it isn't. In this picture, which of these 2 slopes is larger? The one on the left or the one on the right? The one on the right is larger. It's more positive, right? More positive means a steeper line. In this picture, the line on the left or the line on the right? Uh-oh. These slopes are negative. Is the steeper line bigger or smaller? Technically, it's smaller because it's more negative, right? So this is bigger. Hey, wait a minute. As we go from left to right, our slope gets bigger. That means here, slope is increasing. Using the words we just came up with 40 minutes ago. What about these 2 pictures? Say it again. Because I went from a small negative to more negative, or a large positive to a small positive, here, slope is decreasing. And in these 2, it's constant. Okay, hang on a second. Slope is measured by derivative. right? So the slope of f is the thing that's changing. Go back to the definition we wrote down at the beginning of class today. We say that f is increasing if the derivative of f is positive. We say that f is decreasing if the derivative of f is negative. The slope is increasing. What should I be measuring the derivative of? I should be measuring the derivative of f prime. That's the second derivative of f. All of the places where my slope is increasing, if f prime is increasing, then f double prime is positive. The change in f prime. If f prime is decreasing, then f double prime of x should be negative. Let's go back to the pictures for a second. These two, those are where my second derivative is positive. This one curves this way. This one curves this way, right? Okay. If I think about my hand as the curve, I can think about this like our parabola earlier, right? Parabola goes up, but the parabola goes down. The two sides here make up this upward opening parabola, don't they? So I'm going to think of it as going up. The concave side, the side that holds water if I pour it in, is up. These two, it's down. So I can actually use my second derivative to tell me about f. The curviness of f, whether it's curving upward or curving downward. We're actually going to use those phrases. So when my second derivative is positive, I have a concave up original function. I have an increasing derivative. If my second derivative is negative, I have a concave down original function, and I have a decreasing derivative. I'm going to give you my favorite mnemonics in the entire universe. These memory tricks I learned 40 years ago. If my second derivative is positive, my graph is concave up. If my second derivative is negative, my graph is concave down. What's missing? If my second derivative is 0, my graph is flat. And doesn't that make sense right here? If the slope is constant, the derivative is constant. Something whose derivative is something that is a constant, its derivative is 0. When we said we had a first derivative that changed sign, we knew we had an extreme there. And we could tell if it was a maximum or a minimum. When my second derivative changes sign, we have what's called an inflection point or a point of inflection. I have heard that word before, not in math classes. Who's taking a foreign language this semester? What's an inflection? The way you say things. It's making sure you put the emphasis on the right syllable. It's a stress, a vocal stress. Anybody got a loose leaf sheet of paper? If you pick up a loose piece of paper and try and fold it so that it goes down on one side and up on the other, you get this kind of wiggly spot in the middle that doesn't want to stay where it's supposed to be. There's a lot of physical stress in the paper in that spot. And notice our change in concavity happens there. It's a stress point, an inflection. Wait a second. Here's a function we already looked at. We did the maximums and minimums. We did the extremes. We figured out what was going on. We said this looked like a W. It went down, up, down, up. We had a minimum, local maximum, absolute minimum. So now I can ask, which way is it curving through all of those things? You know what the first derivative is? You should have it written down a couple pages ago. What's the second derivative? What's my second derivative? Each of those has a 12 in it, so I can factor that out. Do I change concavity in this graph? We go down, up, down, up. Do we actually curve in different directions in different places? The only way I'm going to be sure of that is if we have inflection points. So let's see where this is 0. Because that's going to be where we switch from being negative to being positive. So I'm going to do the same sort of sign chart we were doing for the first derivative for the second. First thing I need to do, though, is find the technically not critical numbers. Critical numbers only happen for the first derivative. So they're potential inflection points. Zeros of f double prime. 3x squared minus 2x minus 2 equals 0. Well, crap. Unfortunately, this doesn't factor. Would have been nice if it did, but no. Okay. Well, these are just gross. So let's get some decimals. 1 plus the square root of 7 over 3. Somebody push a button. Tell me what that number is. 1.2-ish. What's the negative one? 1 minus square root of 7 over 3. (0.55). Great. Now I can do my sign chart. 1 minus root 7 over 3. 1 plus root 7 over 3. The only reason I need the decimals is so I pick test numbers that are in the right spot. I want to make sure I'm bigger than 1.2 when I go over here. Let's use 2. I want to make sure I'm between them. Let's use 0. I want to make sure I'm less than this negative 1. I can use negative 1. But if I didn't at least have a decimal approximation, I wouldn't know whether or not I was picking a number in the right section. And now I can plug those in to f double prime. And all I need you to do is tell me whether the result you get is positive or negative.
Here's a line.
Do the what?
Line.
Yeah, absolutely. I just put the chart pieces in for the bottom so I had room. When I put in negative 1, I get a positive result. If my second root is positive, I'm concave up there. When I put in 0, I get negative 24. That is a negative result. I'm concave down there. When I put in 2, I get a positive result. So we do have points of inflection. And if I want, I can use the trace button on my calculator to give you y values. And you can actually give me a point Please notice you can actually put in the number exactly. You don't have to put in the decimal. Although it helps if you put it in right. 1 minus the square root of 7 over 3, not over 2. 2.32. And look at where we are on the graph. We're between a section curving upward and a section curving downward. Similarly, if I do 1 plus square root of 7 over 3, I'm between a section curving downward and a section curving upward. Now we actually got a physical point. That's why we called them points of inflection rather than numbers. And this matches up with the image in my graph. I could do the same thing for our other picture. To find the changes in concavity, because it looks like we're concave up, concave up, concave up, but there's this little twist here, isn't there? So we probably go from going up to going down to going back up. We should have more inflection points here, shouldn't we? But if I go to do the second derivative for this problem, I'm going to have to take the derivative of this. So that's a product rule and a chain rule. Oh no. We'll live. Questions? Anybody notice anything really interesting about the numbers I chose for my test numbers? Lindsay. I didn't pull these numbers out of thin air. Where did I get -1, 0, and 2 from? Son of a... Those are our critical numbers, aren't they? The second derivative, when used at a critical number, gives me more information. Let's just draw a picture. I want you to draw a picture that has a horizontal tangent line and is concave down. Suppose they has a horizontal tangent line and f double prime of A is negative. If my second derivative is negative, I'm concave down. So I have a point with a horizontal tangent line. Here's our point where x equals A, right here. If my second derivative is negative, I'm concave down. Means the graph must be under that tangent line. But the only place I have a horizontal tangent line is where I have a critical number. And critical numbers are where I get extremes. This must be a local maximum. I don't actually need the sign chart. I can plug into the second derivative instead. What if I had f double prime being positive? I either have a mustache or a dimple in my chin. But that tells me where the tangent line is. It's either always below the graph or always above it. I must have a maximum or a minimum. I can use the first derivative and make a chart to tell me about extremes, maximums, and minimums. I can use the second derivative as well. So there's an entire separate test. Second derivative test for extrema. Suppose f prime of A equals 0. So I have a critical number. And I have a second derivative that exists there. F double prime of A exists. If F double prime of A is positive, then a local minimum occurs at x equals A. If F double prime of A is negative, then a local maximum. And if F double prime is also 0, there's a flat spot. This test is inconclusive. So I actually learned a lot of information about F based on what I know about the original function, what I know about its derivative, what I know about its second derivative. So we're almost at the point where I can tell you how to know whether or not the picture I've drawn has all the important information on it. There's a couple other little things I need to do. And one of them goes back to limits. Need to go back to indeterminate forms. There are a couple places where I'm still going to use those, and I need to know what the hell's going on. But that is not today. So I will see you all tomorrow. If you came in late, you need to give me your homework, please do. Otherwise, ta.